My name is Danish Pedersen. I'm a former bioinformatician, now data scientist at the Danish Tax Authority, doing a lot of fun stuff there. I'm going to talk about one of my personal projects, so this is just spare time fun, but it has proven to be quite popular. So the topic of my talk is an R package called gggraph, which is a visualization of or visualization framework for network graphics. And before I get too much into it, I had a slight number of misfortunes before I came here. This is just a spare time project, so I'm not paid by my company to be here, and my contingency plan for getting funded to be here kind of fell off after 2 weeks before I came here. So I crowdfunded my stay here, and all of these people were surprisingly generous in paying me for coming, and Plotly was very generous in giving the last couple of dollars. So thank you so much to these people. I can't be too grateful for that. So what have they paid for? Well, I'm going to talk about gggraph, and gggraph is an R package. It's built on top of ggplot2, and this is quite a diverse crowd, so not all of you are using R, unfortunately. So not a lot of you might be familiar with ggplot2. So I'm going to talk just shortly about ggplot2 and talk about why ggplot2 is such a fantastic thing, because it directly translates to why I think gggraph is such a fantastic thing. Then I'm going to give my short layman for the state of analytical network visualization, which is kind of what drove me to develop this, and we'll dive into gggraph, showing some examples, talking about how it's built up, and then talking a bit about the roadmap, and hopefully there'll be time for some questions and discussions. Due to the name, if I don't have something better to show, I'll just show a bunch of giraffes instead of showing an overly complicated hairball network visualization. So this just signifies that I have nothing better to show you at this slide. So ggplot2. This is my elevator pitch for ggplot2. Hadley Wickham is not here to give it, so I'll try. The whole idea of ggplot2 is to define a short but comprehensible vocabulary for plots. So define what we mean when we talk about an analytical plot. What are scales? What are the geometric representation of data, and so on and so forth. And then try to map this vocabulary to small functions that do this sort of thing well. And once you have these functions and have a way of composing these functions, you can kind of speak your plot. And this is really, really powerful, because you don't have to learn like 3,000 different kinds of functions to plot 3,000 different kinds of plots, because they're all assembled based on a very intelligently built up system. So ggplot2 itself is really powerful in itself. It provides quite a huge coverage of base functionality, and it's I think I'm not wrong in saying that it's probably the most popular way of plotting things in R right now. But it is also kind of acknowledged that it can't do anything or everything. And so they have defined an extension mechanism last year, I think. It defines an extension mechanism for other people to kind of chip in and say, well, this is not part of ggplot2, but I really want it. So you can just develop it yourself. And this is what I've been using to develop gggraph. So just to show a bit about how ggplot is in action. So this is quite a standard ggplot plot. I'm not saying that this is a fantastic way of showing this data set, but just showing some of the things that it can do. And the code to the right shows how you build it up. So you define a plot, you put in some data, you put in some mapping between columns in your data and different aspects of your plot. So we are plotting carrots on the x-axis and the price of the diamonds on the y-axis. And then we add some layers. So I think, well, I want all the points on it. I want a scatter plot. So you add a point layer using the geoPoint function. But yeah, well, I also want some smoothing done, so just to see the general way the data behaves. So I'm adding another layer called gmsmooth. And then, I want to not show everything in the same plot. So I want to add a lot of small multiples, and we're using this faceting verb in R, which splits out your data into small multiples based on the cut column. And then we can define things like color, the color scale. We can define things like the theming, so these are not things that are directly related to the data as such, just how the end result is presented, and we can add decorations like titles and captions. I hope that it is clear that this kind of API makes it very, very easy to switch in and out of different plots, so I can just remove the geom points to avoid having a scatter plot. It's not like we have a scatter plot with a smoothing function. We can just assemble our plots line by line, and we can kind of speak it in the sense that I want a plot with points and smooth, and I want it split out. So this has been hugely popular in terms of making exploratory graphics, because it's so easy to iterate over the plot that you want to end up with. So you can just add things onto it, you can change stuff, you can take it out, and so on. So I hope I have convinced you that ggplot2 is a fantastic thing with this very, very small introduction. Why do we plot networks? Well, a lot of the network plots that we're seeing, especially in biology, is we want to show our data. We want to show that we have complex stuff, basically. So we see a lot of hairball diagrams just showing everything that we have. Look, I have complex stuff. Please fund me some more. And this is okay to do, but it's not really investigating into things. We also make eye-catching graphics. It's a great way to engage users and engage people into what you're doing. We also make them to kind of convince ourselves that our notion of the topology of our data makes sense. So we can make a network plot, and we can color the nodes, and we can say, well, this kind of looks like what I expect it to do. So my idea about my data probably is correct. And we can also, for very, very simple network structures, we can also just plot them to show the relationship. Network plots usually don't scale that well, but for small networks that can be a really, really easy way to show the topology of the network. What all of this is about is that, well, network visualization is often about communication. All of this is about communicating either with your peers, with your user, or with yourself, instead of actually engaging in an analytical workflow. This is of course not always like this, but I'm fairly certain that a lot of network visualization is done with some of these things in mind. So why don't we analyze with network visualization? There's a couple of problems in doing network visualization that kind of limits the analytical way of working. Some of it is just kind of inherent to network visualization. So many of the ways that we are laying out nodes on a 2D plot is not stable. So some of them starts off on a randomized position and try to optimize for a local maximum. And next time we plot it, it looks different, which is really, really annoying if you're trying to kind of iterate over an idea. And another problem is that, well, a lot of the tools are really not meant for this. So there's no lack of tools for making network visualization, but a lot of these tools are made for making these communication charts, and it kind of hampers the analytical workflow in some sense. We have problems with overplotting with a lot of complex networks, so we have this hairball diagram, which is, well, you can kind of hear it in the name. It's not really a positive thing, it's just a kind of a mess of edges and nodes, and we can't really get that much information out of it, and this is all due to overplotting. And furthermore, in this, I might only speak for the R world right now. I don't know much about Python and other tools, but there's kind of a fragmentation of approaches. So what ggplot2 is doing so well is that it has a unified API for doing a lot of different types of plots. But for making network plots, you might want to make these kind of node edge diagrams, and you can do that in a package called iGraph. If you want to transition over to something else, like a Hive plot, then you need to use another package which implements another API, which implements another. So every time you kind of want to change the way you're looking at data, you have to adjust for a new API, a new way of doing things. And this kind of mental transition really makes a lot of people not wanting to iterate over how you want to show your plots. So this is kind of my go into the gggraph. So I, of course, think I can solve some of this at least. So gggraph is my package for at least trying to make a unified API for doing a lot of network visualization. It's an adoption of the whole idea behind ggplot2 for relational data. So it's built on top of ggplot2. All of the stuff that you're used to doing in ggplot2 works quite well in gggraph. So it's not a separate package just implementing the API. It's built on top of ggplot. And it tries to create a unified API for all network visualization approaches. Of course, that's a tall order. It's an area that's constantly getting new kinds of ways of doing things, but that's at least the end goal. And as a short aside, it's also trying to support all the different types of network object or data object types that we have in R. So there's a lot of different ways of storing and handling network data. If you have a hierarchical clustering, you have a dendrogram object or an H-cluster object. If you have a more kind of standard graph object, you can have network class or an iGraph object, and so on and so forth. And the user should really not care about that. So they should just put in this data structure into gggraph and work on it as if they were all the same. So this is a focus on static plots. This is different from a lot of the things that we have seen today, but I'm planning to have some Plotly integration at some point. But also I really feel that a fantastic static plot can be just as powerful as a not so fantastic interactive plot. So I really want to focus on making as powerful static plots as possible. Yeah. It's available on CRAN and it's developed on GitHub, so you can just download it, play around with it. There's a lot of documentation, some vignettes, like tutorials to go through, so I hope it's quite easy to begin to use. But of course, now I'm here, I can just begin to show you a bit about how it works. And the fundamental idea behind gggraph, what it adds on top of ggplot2 is a trinity of verbs or ideas about network plots. There's layouts, which is position of nodes on a 2D surface. We have the nodes and we have the edges, and these are kind of the new things that are not really part of ggplot2 at the moment. These are things that are unique to network data, so it's not really concerned Hadley Wickham during the development of ggplot2. So how are these implemented in gggraph? Well, the layout is something that you define globally. So instead of initializing your plot with a ggplot command, you initialize it with a ggraph command and you specify the layout. And then the layout will be just global for everything that you add below that. So you don't have to think about the layout after the fact that you have defined it. The nodes and edges are really the entities, the layers that you want to add. So there's a family of geom node geoms and there's a family of edge geoms. All doing different kind of stuff. So when you just write your function, it kind of look like this. So you just assemble it. This is kind of the simplest case. And you can add additional information as we saw with the ggplot2 functionality. So the edges has their own color scale, so you can color edges differently than you can color nodes. And yeah, there are some faceting that are specific for gggraph as well. So just plotting in something, I said that I wouldn't show too many hairballs, but I'm promising I'm going to iterate on this and then probably make it a bit better. But just to show how it plays out in real life, so we're specifying a layout. This is Kamadi-Kavi layout for positioning nodes in space. And we just want to show straight lines, so we're using the geom edge link function, and we just want to show nodes as points, so we're using a geom node point function. And then we're adding a theme graph which remove a lot of the things that you really want in your normal data visualization, like axes and so on. They are pretty meaningless in network visualization, so I've just kind of made a theme that removes all redundancy. So layouts, what are they? Well, layouts are a conversion of your data structure, the network, the relational structure in your network into a position of the nodes. But in the context of gggraph, the layouts also do other stuff, so it can add additional information to the nodes. So for instance, if you want to plot a tree map, it's not sufficient to just know the position of the rectangles. You also need to know the dimensions of the rectangle, and this is also part of what the layouts are doing. Furthermore, the layouts are unifying the data source for subsequent plotting, so it takes in all of these different types of data objects, and it kind of makes a unified representation of this. This last bit is going to be pulled out of gggraph into another separate package called tidygraph that I'm developing, which will take care of a lot of data manipulation at the network level. But that's a topic for another talk. The nodes are kind of boring in a sense. It's really the most ggplot-like or general plot-like feature, because if you remove edges and just plot the nodes, you kind of have a scatter plot in some sense, just with arbitrary axes. So there's not a lot to say about it, but there are some additions. So all of the node geoms have the position preset because it's given by the layout, so you don't have to specify that the x-axis maps to this and the y-axis maps to that. It's all happening under the hood. It also comes with a filter, so it's very easy to only show part of the nodes directly based on the data that you have. And it also comes with some niceties from some of the other packages that has been developed for ggplot2. So for instance, you can label your nodes, and you can make sure that they don't overlap by using the ggrepel package automatically. And as a short aside, sometimes nodes are all you need. So usually you think that edges are what's really showing the network structure, but there are some layouts that are actually just using nodes and using the position, like tree maps or icicle plots or sunburst charts. The inherent relationship between the nodes there are defined by the node's position as well, with inclusion or just position. So sometimes you just want to plot nodes. Anyway, the edges are where fun stuff begins to happen. So there's a lot of different ways to plot edges. Many types, many shapes. They have their own separate scales, so you can color and size edges separately from nodes. And they have access to the node data that they are connecting. So each edge will know the different data points of the nodes, the terminal nodes that they have, and you can actually interpolate between different node information between the edge, so you can have a smooth color scale between from the edges between two nodes, node informations. It also comes with a filter, and it has labels that automatically rotates based on the dimensions of the plot. So yeah, and they can get capped around the nodes. So if you want to draw arrows, for instance, you don't want them all to kind of stop at one point. You want to have them to stop a bit away from it, to not have this overplotting of arrowheads. So it comes with a lot of niceties. And then there's all the rest, because it's not all there is to it. There's a lot of different faceting functions for creating small multiples of graphs. There's this network-friendly theme that I talked about. There's also the whole notion of connections. So sometimes you want to show a relationship between nodes that is not part of the network structure. Maybe you don't want to have this connection influence the layout in any way, but you're still able to draw it using the connection interface that we have. We have separate guides for showing edge direction, and there's a lot of this stuff has been implemented in C++ underneath, so it's quite efficient and fast to do, at least the things that I'm in control of. So let's revisit the plot that we saw before. That should be happening something. Yeah, there you go. So this plot is actually a plot of my small Twitter world. So this is all the people I follow and how they interrelate with each other. I thankfully don't follow that many people, so it's quite easy and manageable. So there's 116 nodes and around 2,000 edges. So this is a horrible plot. I hope we can all agree. It doesn't really say that much about anything, except that I have complex data. So what can we do? Well, one of the things that we can do is that we want to format our edges a bit. So a Twitter network is directed because I follow someone, they don't necessarily follow me. So edges, the edge direction have a meaning. So we can signify this by adding arrowheads, but arrowheads adds a lot of clutter. So we don't always want to do that. Another way you can do it is by adding a gradient over the edge, and this is what we can do here. So we're mapping the color to the index of the edge. An edge is actually exploded into a lot of small points, and the index just signifies the position along the edge. So if we add a color gradient over the index, we get a nice gradient over the edge. We can set width and alpha and so on, and we can say, well, how do we want this color gradient to be by adding an edge color a scale to it. And we're just going to go from white to black. So with these few lines of code, we have a bit more manageable network plot. I would argue that this is still not a fantastic plot, but just showing some of the things that you can easily do with a few lines of code. So maybe I want to show the ones that are actually following each other, so the true friends of my networks. And we can do that by just adding another layer of links on top. So we add a new geom edge link on top of the other link, and we use this filter. And I've already added whether they are mutual or not to my dataset. So I just filter on whether or not this edge is signifying a mutual relationship. And I'm adding another color and so on. And what we get now is a kind of a different picture. So it's quite easy to add new layers to your plot and show different relationships. So now we can begin to see that, well, we certainly have a lot of interrelationships between those this big cloud of points there. But we also have some other smaller areas where people really seem to know each other and interact a lot. Trying to do something a little bit better, well, we can color our nodes to see, well, what are these nodes anyway? And I have just, because I don't follow that many people, I've just sat down and assigned a type to them, whether they are data visualization or a data scientist or a statistician and so on. I know this is not very scientific and there's a lot of overlap, but just for the sake of experimentation. And I'm going to size them based on the followers count. Of course, I follow a few people that have like millions of followers, so I'm just going to add a small transformation to the size, so it's log transformed down here. And now we can begin to see something emerge. So we have this area over here, which is the programming crowd. We have this cluster over here, which is the visualization crowd. We have an area over here, which is the art crowd. I follow someone's doing generative arts, and they seem to kind of know each other quite well. And we have statisticians that are kind of all over the place. And this kind of makes sense because statisticians are usually engaging a lot with both programmers and visualization people and so on and so forth. But let's try to zoom in a bit on these different types of people. And we can quite easily do that by just adding a facet graph to it. So what we're saying is that I want to split out my network plot into small multiples, and I want the rows to signify the type of node that's there, and I want the columns to signify whether the edges that it's showing are mutual or not. So how's that going to be? Well, with a few lines of code, I've actually exploded my graph into a lot of subviews, and of course this is not perfect for the granularity of the resolution of the screen, but we can still see some things here. So what was not really apparent before was that, well, in statistics we have a small group of 5 people that seems to know each other quite well, and the others kind of flowing around a bit. This was kind of obscured by the overplotting that we had before, but it's really apparent now that we have split it out. The same can actually be said by the Bioinformatics crowd. So we have an area over here where people seem to love or like each other, and maybe also love, I don't know. And we have the others that are kind of floating around. So for these bigger clusters, we don't really gain that much insight, but for the smaller things that really were masked by the size of our network, we can actually begin to see some stuff happening. So let's try to do something else. Let's try to use another layout. And I'm going to make a Hive plot. The Hive layout is kind of an esoteric way of showing networks, but it's a rather fun way of showing it. It takes a lot of more parameters, so the gggraph calls gets a bit more complicated. But other than that, we're not doing that much. We're changing the edges to geom edge Hive. So instead of drawing straight lines, we're drawing some edges that are bent and look nicer on a Hive plot. But other than that, there's not really that much we need to change in our code to get a fundamentally very, very different plot. So this Hive plot shows the split between programmers and statisticians and visualization, and each edge is also split whether or not I think they use R. This is, again, not very scientifically, it's just I seem to think that they at least use R a lot in terms of what they tweet about. And what we can see is actually that, well, statisticians, not surprisingly, seems to follow a lot of programmers, but usually the programmers that are using R. Probably because these programmers are also a bit statisticians, because they're using R, so general purpose programmers tend not to use R that much. And we can see the same with the visualization crowd. They seem to usually just follow programmers that use R. So some of these things were not apparent in the other plot due to overplotting, but by adding this extra kind of information and adding some sense to where we position the node, we can begin to look into this. And again, not changing our plot code that much, so it's quite easy to iterate on this. Let's just try to show something else. So I'm trying to show a tree instead. My network is not a tree in itself, but I can do some community detection, which are sometimes hierarchical. So I just did a community detection algorithm on my network, and what I got out was a dendrogram object, but it doesn't really matter because you can just feed it into gggraph. And I say, well, give me the layout as a tree, and I just want to filter the nodes, so I'm only plotting the leaf nodes. Other than that, I'm really not changing anything in my code, and I get this, I wouldn't say nice plot, but just to show how easy it is to change around and do stuff. Just to show you can also use different edges on tree plots to get a more organic look. And just once again to drive home the point that it's so easy to change the way fundamentally of how your plot looks. I'm going to show this as a tree map instead. And the only thing I really have to do is to change the layout to a tree map and say, well, now I don't want my nodes as points, I want them as tiles. And you get a tree map. So it's fundamentally very, very easy to iterate over stuff and try out different stuff. I'm not saying that I've gained a lot of insight on this example, but it's just very, very easy for you to change the way that you're looking at stuff in an iteratively way and explore your data in that way. So, the roadmap. So where are we going? Well, the biggest kind of problem or thing I need to look out for is that, well, I want an API that is unifying for everything. And that's, as I said before, that's a tall order. There's a lot of layouts that I don't support right now. I think I support more than the general package in R, but there are new layouts that I want to incorporate. There are matrix layouts. I want to port the D3 layout because that's actually a really nice layout algorithm. There are different edge types that I haven't supported yet. So there's bundling of edges, or there's routing of edges around nodes and so on. And there's node types that I haven't supported yet. I also want to add some kind of node annotation, so it's easy to draw shapes around nodes that are from the same distribution or whatever. And I want to support some way of having multiple layouts and compose your graph using multiple layouts, or have small multiples using different layouts or such. So furthermore, as I talked about, tidygraph is an ongoing development that is going to take out some of the complexity of the gggraph code. And I've talked to Carson from yesterday about how we can really add Plotly integration to add these kind of standard interactive features on top of gggraph. So all of this is available on GitHub, and the roadmap is also available on GitHub, so please interact there. I'm really, really eager to hear about new ideas of what people really want in network visualization, so just open up issues and I'll happy to respond. Thank you. Questions? No.
So do you worry when you're doing like the small multiple, like you're actively chopping through edges when you do that, right? Have you thought of indicating how many edges you are sort of breaking in some way?
No, that's quite an interesting question. So there's support for adding a marginal plot at the side in the same way that's possible in ggplot2. So you can have for each row and for each column, you can have the total of the plot, and there these missing edges will be there, but they are not indicated as being missing on the other plots. So maybe that it could be possible in some way to indicate in these marginal plots where the missing edges are. That's quite an interesting idea.
In the packages, can you also visualize the edge weights, or if not, do you have any plans to include that? I saw directionality, but not the actual weight.
You can do whatever you want. So edge sizes can be changed, the color, the whatever, the opacity of the edges. So whatever you really want to encode into both the edge and nodes are really possible. So it's just imagination.
Did you have any deterministic layouts in your examples? And also, what about network modules?
So yeah, there are some deterministic layouts. So for instance, Hive plots are deterministic in the sense that they are actually positioning nodes based on the information that's attached to the nodes. Some of the hairball layouts are also deterministic. So the ones that I've used, the Kamatekabi is deterministic. Not necessarily optimal, but it always returns the same layout. So for the non-deterministic layouts, you can always kind of manage it by setting the randomized seed before you're doing stuff, but that's kind of a burden for most people. Or it's not that is difficult in any way, but while doing iterative work, it's kind of annoying that you have to do it. So